Hello everyone. So I'm going to cover right now section 9.3. We're going to talk about intersection between two planes. We already know all three possible configurations from Unit 1 if you have two planes. If your first plane is called phi1 and your second plane is called phi2, suppose a Cartesian equation of phi1 is a1x plus b1y plus c1z is equal to d1, and that your second plane is given by a2x plus b2y plus c2z is equal to t2. There's three possible ways that these two planes can be configured in space. They could be parallel but disjoint, so they're not touching each other. They could be parallel and actually be on top of each other, so that's the case when they're equal. Or it's possible that the two planes are non-parallel, and then in that case they intersect on a line. And we've seen this already in Unit 1, but now what we want to do is see the connection between the three possible configurations between two planes and the type of solution that you get if you're creating this system of linear equation where both equations are those plane equations coming from phi1 and phi2. All right, let's start with a small recall. If you start with a point P where the coordinates are k1, k2, and k3, in a plane phi where the Cartesian equation is ax plus by plus cz is equal to d, then if you want to check that if P is inside phi, what you need to do, you need to take the x coordinate of P, which is k1, and you plug it into the Cartesian equation, and you replace the x variable by k1. You replace the y variable by the y coordinates k2, and then you replace the z variable by the z coordinate k3. And if you have equality, then P is inside phi. So algebraically, when P is inside phi, this will be true if and only if A times k1 plus B times k2 plus C times K3 is equal to D. If you have equality, then it's inside. If you don't have equality, then it's outside. So in other words, if P fits inside the plane, or if P is inside the plane, it is a solution of that equation. Of course, the Cartesian equation of a plane is a linear equation. So we have this really tight relationship between is P inside the plane versus is P a solution of the linear equation ax plus by plus cz is equal to d. And that's the relationship that we're going to exploit to make that connection between the system induced by plugging the two Cartesian equations together and the general solution. So let's look at the first case, the case when two planes are parallel disjoint. So in that case, for that configuration, so we have two planes, phi1 and phi2. I drew my phi1 here in blue and my phi2 here in red. These two planes are parallel disjoint. Of course, I'm not going to draw it here, but if you draw two normal vectors, one for phi1, one for phi2, you could check right away if these two planes are parallel just by checking if these two vectors are parallel. But in the disjoint case, what happens is that if you pick any point in phi1, so let's pick a point in phi1, well, that point in phi1 here in blue is not, of course, in phi3, and of course if you pick a point in phi2, let's call it p2 here, it's not in phi1. So of course p1 is a solution of phi1, but p1 is not a solution for phi2, and vice versa. P2 is a solution of p2 but not a solution for phi1. So this means that if you look at the system of linear equation that you get by combining phi1 and phi2 together, you will not have any possible solution because there's no point that fits in both phi1 and phi2 at the same time. So there's no triplet that will be a solution for phi1 and phi2 at the same time. So this means that the intersection between phi1 and phi2, of course, is empty, which will correspond to no solution for your system of linear equation. Now in the second case, when the two planes are parallel, equal, what happens is the following. When we look at our two planes, so again here I drew phi1 and phi2. So I drew phi1 and phi2 in blue and red respectively. And when they are parallel equal, of course in unit 1 we saw that they're parallel equal if n1 is a multiple of n2, and if that multiple carries on to the d part, so if d1 is a multiple of d2 with the same multiple. So when they are parallel equal, so this means that at the intersection you have both planes. So both planes are exactly the same. So here, just for visual aid, I drew like rectangles, like one going northeast and the other one just being like horizontal, just so that we can see that when they are equal, they overlap on this purple region. And in particular, what you can notice is that if you have a plane at the intersection, so you can pick a point that lives at the intersection, and then what you can do, you can draw two vectors. So if you have WV here, and let's say W here, you can see that the plane generated by that support point P and those two generators V and W respectively is going to be what lives at the intersection. So here the intersection of phi1 and phi2 is given by P plus T times V plus S times W, where T and S are just real numbers. So this means, from the point of view of the system of linear equation induced by bundling the two Cartesian equations phi1 and phi2 together, that when you're going to solve it, you're going to get infinitely many solutions, because there's infinitely many points that lives between phi1 and phi2, because the intersection is either phi1 or phi2. But what's really crucial here to understand is that we have two free variables, S and T. So we have two, so we have T and S. So you're going to get infinitely many solutions, but with two free variables. So your system will have infinitely many solutions. But, and that's the important part, with two free variables. That's the key part here, is we have two, because the third case will also have infinitely many variables, but we will only have one free variable, and you'll see that right now. So finally, what happens when the two planes are non-parallel? So finally, what happens when we are in the third case? So when the two planes are non-parallel, well, in that case, let me just zoom in first. In that case, so case 3 here, so I drew again phi1 in blue, phi2 in red. So the two planes are non-parallel. Normally, in unit 1, when you have the two Cartesian equations, you check if two planes are non-parallel by checking if the two vectors, n1 and n2, are not multiple of each other. But now let's think about it in terms of system of linear equations. So here, geometrically speaking, when they're not parallel, they will intersect. So the two planes will have an intersection, and that intersection here will be this nice line here. So at the intersection, we have this nice line that I'm drawing right now in purple. And when we have a line, this means that we have a point. Let's say that this is one of the points I could choose, P, and we have a vector. I'm just going to slightly change the color here so that we can visualize it. And we have a vector. Normally, one way to compute a good vector that will generate that line is by taking the cross product between n1 and n2. This is what we used to do in unit 1. But now we're just thinking about it in terms of system of linear equation. So when you're going to compute the general solution of the system of linear equation induced by bundling the equation of phi1 and phi2 together, you're going to get infinitely many solutions because there's infinitely many points that lives at the intersection between phi1 and phi2, but you only have one free variable in your system, in your general solution, because your object that lives at the intersection is just one-dimensional. So the intersection between phi1 and phi2 is a line. Typically, we call that line L intersection. So you can write L intersection, or if you want to see it as a vectorial equation, you could say it's P plus T times V, where T is a real number. So here, when you're going to solve the system, you're going to get, again, infinitely many solutions, but you're going to get only one free variable. Of course, that one free variable is T here. So that's the distinction between case 2, where the intersection is a plane, versus case 3, where the intersection is a line. It's two free variables in case 2, and it's one free variable in case 3. Let's do our first example, example 9.3.1. So we need to describe the configurations between the following pairs of planes, and we'll be using the general solution to make that conclusion. So for A, we have phi1 is equal to x minus y plus z is equal to 2, and the second plane is phi2 equal to 2x minus 2y plus 2z is equal to 3. Of course, just a small remark here, but if you do it the old way, to find a configuration for the first plane, you would say that n1 is 1 minus 1 and 1, and n2 is 2 minus 2 and 2, and obviously because 2 times n1 is equal to n2, you can conclude that that the vectors are parallel, so n1 is parallel to n2, and then you can conclude that the two planes are parallel. Phi1 is parallel to phi2. But if you look at the d values, so if you try to multiply 2 by d1, and d1 here would just be 2, and you compare this with d2, and d2 here is obviously 3. Of course, these two quantities are not equal, so the final conclusion is that phi1 and phi2 are parallel disjoint. So that's the old way. And of course, on the test, typically I would not force you to do one specific method versus the other. But let's redo this question and find that these two planes are parallel disjoint using the general solution. So first, you create a system of linear equation. So the system that we're going to construct is the following one. So the first equation is x minus y plus z is equal to 2. And the second equation is 2x minus 2y plus 2z is equal to 3. So now we're just solving a system. So the first thing you always do is you associate to that system of linear equation its augmented matrix. So 1 minus 1, 1 augmented by 2, and then 2 minus 2, 2 augmented by 3. Here it does not take much to put this in row reduced echelon form. So the first pivot will be in the first row, and it's already a 1. So the operation that we're going to use here is that row 2 will become row 2 minus 2 times row 1. So this matrix will be equivalent to not touching the first row. So I can rewrite the first row quickly, but carefully. So 1 minus 1, 1, 2. And then 2 minus 2 times 1, you get your 0. minus 2 times minus 1, that's minus 2 plus 2, which is 0 again. 2 minus 2 times 1 is 0. And then 3 minus 2 times 2, you're getting minus 1. At this point, you could stop, and I'll stop here because this is not asking me to put things in row reduced echelon form. The first pivot is on the first row, first column. The second pivot is on the second row, but in the augmented column. So here you can see that the rank of A is 2, but it's not equal to the rank of AB, which is 3. Sorry, what am I saying? The rank of A is 1, which is not equal to the rank of AB, which is 2. Therefore, Phi1. So therefore, first you can talk about the general solution. So no solution. And then the final conclusion is that Phi1 is parallel to Phi2, but disjoint. So we're just making this connection, okay, between no solution and the fact that the connection between no solution and the fact that these two planes are parallel, disjoint. Next example, B. So we have the same Phi1, so x minus y plus z is equal to 2. But now the second plane is Phi3, 2x minus 2y plus 2z equal to 4. Of course, just looking at these two equations, you should just see that they're equal, because if you multiply the whole equation by 2, you're going to get the second equation, Phi3. So when you get that, you can get this second equation just by rescaling it. Automatically, we know that Phi1 is equal to Phi3. But let's do it using the general solution here and see that again we are getting that these two planes are equal. So here we go. So again, as usual, the first thing you do is you construct a system of linear equation. So we have x minus y plus z is equal to 2, and 2x minus 2y plus 2z is equal to 4. The augmented matrix of that system is 1 minus 1, 1, augmented by 2, and 2 minus 2, 2 augmented by 4. So my pivot in my first row will be in the first column. It's already a 1. The goal is to eliminate that 2 under here. So the operation is row 2 will become row 2 minus 2 times row 1. So it's the same operation as earlier. They're very similar examples. So this will become, so I'm not touching the first row, so I can rewrite it quickly but carefully. So 1 minus 1, 1, 2. And then if you do the multiplication, the elimination, 2 times 2 minus 2 times 1, minus 2 times minus 2, minus 2 times minus 1, and 2 minus 2 times 1, and 4 minus 2 times 2, you're getting a row of zeros here. So you have your matrix. This one is actually in row reduced echelon form, since we just care about the solution. The type of solution, we don't normally care about putting it in row reduced echelon form, but since I'm here, might as well write the general solution, because there's a nice remark here. So we have the first column for x, the second column for y, and the last one for z. So here y and z are pivot free, so these two variables are free. So I will associate to y, let's say s, and for z I will use the parameter t, and then using the first equation, so if I'm calling the first row equation 1, you can see that, so I'll just go down here, equation 1, so remember this is not part of it, so equation 1 leads us to x minus y, which is minus s, plus z, so plus t is equal to 2. So if you isolate x, you get 2 plus s minus t. So we have an equation for x. We have an equation for y. And we have an equation for z. So for y and for z. So when you bring everything together, you get that, let's go back in blue here, you get that x, y, z. And here I want the canonical form. So x is 2 plus s minus t, y is s, and z is t. So if you break this into the canonical form, you get 2, 0, 0, plus s time, so plus s time 1, 1, 0, and plus t times, so it's going to be tight here, plus t times minus 1, 0, 1, where s and t are real numbers. And here, this is very, very important here, like when you write the canonical form, you see that this equation, this general solution of this system of linear equation looks like the vectorial equation of a plane. What I mean by this is that when you look at it, you start with a triplet with no variables here. That's your support point. That's what we could call, let's say, a support point. So you could call this part the P, the S times the other vector. This could be the V vector. So let me just highlight that. So that would be the vector V. And then the last vector, you could call it W. So having P plus S times V plus T times W, that's the vectorial equation of a plane. So all of this, just to say that, in conclusion here for that example, that the two planes are equal. We have two free variables. They are equal. Not only do we know that they are equal, if you want actually to go from the Cartesian equation to the vectorial form, the vectorial equation of the plane, you could just use a system of linear equation where you're only using, like let me just highlight this, let's say in orange. Like suppose you just want the vectorial equation of the Cartesian equation of the first plane, you just need to use a matrix with one row, and then you just write the general solution in canonical form, and then you're going to get your general solution in canonical form is going to be the vectorial equation of your plane. So next example, last example, C. So we have the same phi1, x minus y plus z is equal to 2, but now phi4 is x plus y plus z is equal to 2. Again, just as a remark here that I'm going to write in green, so n1 is equal to 1 minus 1, 1, but n2 is 1, 1, 1. So that's your n2, and of course, these two vectors are not multiple of each other. So because they're not multiple of each other, so let me just use a case. So n1 is equal to 1 minus 1, 1, and then n2 is 1, 1, 1. So if you wonder, is n1 a multiple of n2? It's not a multiple. So we know right away that the two planes are not parallel. Well, sorry, normally the first thing you should do is comment on the vector. So because n1 is not a multiple of n2, then you can say that n1 is not parallel to n2, and this means that the two planes are not parallel to each other. So we get our final. So because the vectors are not parallel, then the planes, the objects, are not parallel, just because n1 is not a multiple of n2. But let's do this. And we know that when they're not parallel, there's a line at the intersection. This is actually, honestly, this third case here, two planes that are not parallel, is the only case where I would use a system of linear equation to have a complete description of the configuration, because the general solution gives you the equation of the line at the intersection. And that's the only thing that is kind of hard to compute just by looking at or harder at least to compute just by looking at the Cartesian equation. So here we go. So final round here for this. So the system first. So just take your time. So here x minus y plus z is equal to 2. And x plus y plus z is equal to 2. So you associate to the system the augmented matrix. So 1 minus 1, 1. So just be careful. Augmented by 2 and 2. So same game here. So we have our first pivot, first row, first column. We want to destroy the one under. So the correct operation is row 2 will become row 2 minus row 1. So this matrix is equivalent to, I'm not touching the first row, so I can rewrite it quickly but carefully. So 1 minus 1, bye-bye. 1 minus minus 1, you're going to get 1 plus 1, so you're going to get 2. 1 minus 1 is 0, and 2 minus 2 is 0. So since we're here, might as well put this in row reduced echelon form. So my pivots so far, first row, first column, second row, second column. I want to make the second pivot the 2 into a 1, so I'm going to rescale that row. So here I'm going to say that row 2 will become 1/2 row 2. So this will create a new matrix equivalent to it. So my matrix is going to be not touching the first row. So I can rewrite it quickly but carefully. 0, 1, 0, 0. Now, right now, both of my pivots, first row and second row, are both equal to 1. But there's this extra minus 1 here. If we want to put this in row reduced echelon form, we could solve it at this point. Okay, but normally on a test, I will ask for the row reduced echelon form anyway. So this is, so if I want to destroy the minus 1 here, the correct operation would be to say that row 1 becomes row 1 plus row 2. So since I'm not touching the second row, I'm going to rewrite the second row quickly but carefully. Of course, I'm going to get a 0 here. And because of the 0 under, the first one is not going to change. 1 minus 0 is going to stay 1, and 2 minus 0 is going to be staying as 2. So now my matrix is in row reduced echelon form. Let's write together the general solution. So first column is for x, second column is for y, and the third one is for z. There's only one column with no pivot, and it's the z column. So z is free here. So here we go. So z is free. There's only one free variable, so we know that we have two planes that are parallel disjoint according to that little theory that we have on the previous page. But let's write the general solution. So if I call my first equation E1, I'll call it E1. So first equation is E1. So I know Z is free. So from my first equation, I can say, so remember, it's just I can say that x, so I'll need two equations here, sorry. So this is my second equation. So let's do E2 first. So from E2, you can conclude that y is equal to 0. So we have 0x plus 1y plus 1z is equal to 0. So we get a value for y. Remember, z is free, so I should have done this first. So z is equal to whatever, let's say t, a real parameter. So we know z is free, so we just assign to those free variables parameter. And then if you look at equation 1 is x plus 0y plus z, which is t, is equal to 2. So x is 2 minus t. So we have an equation for x2. Now we just assemble everything. So variable assemble. So we have x, y, z is equal to 2 minus t, y is 0, and z is t. So you break this into canonical form, so you get 2, 0, 0 plus t times minus 1, 0, 1, where t is some value in r. And now, again, very important remark here, just to feel this. So because there's only one free variable, because we have infinite many solution with only one free variable, the conclusion is that phi1 is not parallel to phi4. But when you have two planes that are not parallel at the intersection, we have a line, and actually the canonical form of the general solution is the vectorial equation, or a vectorial equation for the line where the support point, so if I use some yellow here, the support point would be 2, 0, 0. So here, so this would be the P, and then the V part. So the generator V here would be minus 1, 0, 1. And this is one of the reasons why we are so obsessed, or I'm kind of pushing this on you to write the general solution in canonical form, because it gives you a very nice link between the geometric description of the general solution and like if you just look at the regular equation, you might not know what's going on, but then when you see a triplet plus t times something, then you know, that's just like the equation of a line. So the general solution gives you everything at the intersection, and then we see here it's a line, and that corresponds to that third configuration where two planes are not parallel. And that's it for that section. Bye-bye.